Hello everyone. Sorry I'm getting this out a little late, but it has been a crazy week. And that is a little bit thick. Usually we're using pencil. Okay, let's see how this works. N is in the set of natural numbers greater than 1. Okay. So, this is going to be this worksheet on prime decomposition. This is worksheet 9, which corresponds to lecture 11. And so I'm going to go through all three of these. I'm not sure if I'm going to do every single type of proof for each one. Like this first one, I'm tempted to just do a direct proof, but I guess we'll see how things flow. And yeah, all right, so I'll just get started. So this first one, we have a natural number that's greater than 1 and is in the set of natural numbers greater than 1. And it has a prime decomposition that's of this form, where n is equal to some prime to a power times another prime to another power, and so on, where all the primes, all the pi, meaning the p1, the p2, p3, ... are all distinct, which makes sense because they're all being raised to whatever power they have. So if p1 and p2 are the same, then we would just add s1 and s2 together and make it into one term. There's no reason to have different pi. Sorry, to have the same pi more than once. So now we want to prove that if n is equal to m squared for some natural number m, then all of these exponents are even. And I think the direct proof of this is actually pretty intuitive. And something that we were talking about in class a little bit is that if n is a natural number greater than 1 and it's equal to m squared, we know that the square root of n equals m. And the square root of some natural number that's greater than 1 is also going to be a natural number greater than 1. So we know that m is not just some natural number, it's actually a natural number that's greater than 1. And maybe that's important, maybe it's not. But yeah, we have m. And yeah, so one thing that we could do with any natural number is we could make a prime decomposition of it. Every natural number has its own unique prime decomposition. So like the number 60 is an example that we used in class, and that breaks into, let's say, just 15 and 4, and it doesn't matter. You could break it into 6 and 10. You're going to come to the same thing no matter what. This breaks into 5 and 3. That's the only way to break down 15. And we could circle these because they're prime. We're going for the most basic units here, which are our prime units. This breaks into 2 and 2. So we end up with 60 is equal to 2 squared times 3 times 5. And notice how I ordered it so that it goes from lowest base to highest base. And we also consolidated the two 2's into one term that has an exponent of 2. Great. So that's how you make a prime decomposition. Every natural number has its own unique prime decomposition. So if the prime decompositions are equal, that means that the numbers are equal. That's just a little bit of background going into this problem. So if we know that m is some natural number, that means m has a prime decomposition. So let's just give it a generic prime decomposition the same way we gave n a generic prime decomposition. So let's say that m is equal to q1 to the power of r1 times q2 to the r2. My temptation is to say to the r2d2 because I'm a Star Wars fan, ... and you could write qk to the rk for k terms. So it's going to be in this form. And now if we take m squared, that is going to be this squared. And when we square an expression like this, we're just going to be multiplying each exponent by 2. And that's something that we learned in algebra. That's just a property of exponents, that an exponent to a power you're going to multiply those exponents. So we end up with q1 to the 2r to the 2r1 times q2 to the 2r2, and that is really bad. I was told that I'd be able to do this on my iPad, like these screen recordings, so this week has been really hectic, so I apologize that it's still of this amazing low quality, but I'm hoping next week to bring a new and improved video series to you guys. So we have m squared is of this form, where each exponent is multiplied by 2. And I think we could already start to see that these exponents are all going to be even, because they're all going to be divisible by 2, and we know that all of these r1, r2, and so on are natural numbers. We're not going to have any negatives, we're not going to have any fractions in these, just because of the nature of how these prime decompositions work. So now this is equal to n, because we have n equals m squared, which is equal to p1 to the s1 times p2 to the s2 ... And now, here's what we could say. We know that if two numbers are the same, that their prime decompositions are also the same. And now, the only caveat that we have to say is 2 squared times 3 times 5 is equal to 3 times 2 squared times 5, because of, I don't know if that's the commutative property or the transitive property. One of you guys, I'm sure, knows. But basically, when it comes to multiplication, the order doesn't matter. So the only thing that we can't guarantee is the same here is the order of the q's and the order of the p's. So we could just make the one caveat, and you see this in Professor Carbone's proof, that she says, so long as we order the qi's and the pi's, you could order them from least to greatest. That's a convenient way of doing it. These are going to be the same. So every q1 to the 2r1 is going to be equal to p1 to the s1, which means that 2ri, each 2ri is going to be equal to each corresponding s sub I, which means, and since this side is divisible by 2, that means it's even. That means that the SI is going to be even. And yeah, my purpose here is not to write out a complete proof, but just to give some intuition for how to think about these proofs. The proofs are all written out in the posted solutions. Hopefully you get a chance to look at those. Okay, so for proof number 2, we're going to let n be a natural number greater than 1 again, and we're going to prove that if n divides n minus 1 factorial, which is equal to this, then n has a proper divisor d that's greater than 1. All right, let's unpack this. So n needs to divide this stuff, which means we have n minus 1 times n minus 2 ... 3 times 2 times 1 divided by n, and this is going to be a natural number. Now, that's what it means for n to divide these things. So that's just me translating this phrase right here, that stuff. So now let's think about what this means. We know that n does not divide any of these factors, any of these terms, n minus 1 or n minus 2 or n minus 3, or any of these hidden terms over here, because n is bigger than all of them. When a number is bigger than a number, it can't divide it. 10 cannot divide 5 and give us a natural number. The opposite is true. 5 could divide 10, but let's say n is 10, hypothetically. It can't divide 5, and it can't divide 9 or 8 or 7, and so on. And what does it mean for n to have a proper divisor? Another way of saying that is that n is composite. Let's say, for the sake of contradiction, that n is prime. That means that its only divisors would be 1 and n. But we're saying that it actually has this divisor that's bigger than 1. And because it's a proper divisor, that means it's not n. That's what that means. So we have some number that is dividing all of these. This is sort of proven by a lemma that we learned in one of our lectures, where the example that we used is we have 6, and 6 does not divide 4, and 6 also does not divide 15. But 6 does divide 4 times 15. And why is this the case? Because 6 breaks down into 3 times 2. It's very important that 6 is not prime for this example. And 4 breaks down into 2 times 2. And 15 breaks down into 5 times 3. So since 6 has this 3 that lines up with the 15 and the 2 that lines up with the 4, 6 does divide the product of these two numbers. And this is something that only happens with composite numbers, as I said. If you have a prime number like 7, 7's only factors are 7 and 1. So the only time it's going to be able to divide a number or a product of numbers is if one of those numbers is divisible by 7. You could see, like, if you have 14 and 6, you're going to get the 7 and the 2 here, and the 3 and the 2 here, and the 1 is irrelevant here. Like, that might as well be crossed out. So it's going to be able to divide this product, 14 times 6, because it divides 14. So tacking on this 6 doesn't really add anything. There's no way for 7 to divide two numbers that neither of them are divisible by 7. So 7's never going to divide something like 12 times 6 or anything like that. You do see this property with composite numbers, which is why we know that n is composite, because the fact that it doesn't divide any of the individual terms, but it does divide the product of all of them, means that n has to be composite. And that's a really important property to remember and also to understand. Hopefully this diagram gives you some understanding of how this breaks down and why this works. It's not really a formal proof, but it's just hopefully an intuition as to what this means exactly and why it's the case. So here we have proof number 3, and here we're going to let p be a natural number that's at least 2, and we're going to say that if p squared plus 1 is prime, then either p is 2 or p is not contained in the primes. And just at first glance, this is a pretty confusing statement, and what I'm already tempted to do is just see what the contrapositive form looks like, just because this looks like kind of a mess, and sometimes when you flip it to the contrapositive, things just clarify themselves quite a bit. So let's write this in symbolic form, and then we'll make this into the contrapositive. So we have if p squared plus 1 is prime, so that's going to be on the left-hand side, p squared plus 1 is prime, then that implies that either p equals 2 or p is not prime. So if we wanted to do the contrapositive, we're going to flip these around and then reverse them. So we're going to say P is not 2 and P is prime, which is already a much simpler statement to understand. P is not 2 and P is prime. So basically P is prime, and we know that 2 is a prime number. So we're just saying that P is a prime number that's not 2. And we could actually even simplify this. This whole statement is the same as if we were to say P is a prime that's greater than 2. That is an equivalent statement, and it's a little more concise. We know that P is a prime, we know that P is not 2, therefore P is a prime that is greater than 2. And it's probably equally correct if you just do a little not equals sign here, not equal to 2. I've never seen that symbol used, so I'm not entirely sure if it's proper notation. So I'm just going to stick with this greater than 2 implies, and we're going to take the reverse of this statement for our contrapositive. That's P squared plus 1 is not prime. And so P is some prime greater than 2 implies that P squared plus 1 is not prime. Now we know that a prime that's greater than 2 is some odd natural number. So we know that it takes the form of some odd number. So we could say that P is equal to 2n plus 1. That's our generic odd number. And we're going to qualify that n is a natural number. That's always important to remember when you're writing a proof, is to define your terms, define your variables. So P squared plus 1 is equal to 4n squared plus 4n plus 1 plus another 1, so plus 2, which is equal to, we could factor out a 2. So let's say it's equal to 2 times 2n squared plus 2n plus 1. And there's a reason I'm doing that. There's a reason I'm factoring out this 2. And we want to say that this is not prime. The fact that we're able to divide out a 2 and we still have this natural number in here means that it's not prime, and that is the proof. And so I know that in our problem it says give a direct proof, proof by contrapositive, proof by contradiction. I think that the proof by contrapositive is the easiest to see. And again, I'd be happy to discuss any of the other proofs with you guys. But I do think that this problem lends itself most to a proof using the contrapositive form. And hopefully when you see problems that look really confusing and are kind of, when the then statement has choices, oftentimes you want to go with the contrapositive and make this the if statement. It's just a lot easier to deal with. It's a lot easier to deal with complications on the if side of things than the then side of things. Hopefully that's just like a good little piece of wisdom that you could take with you, and maybe it'll help you solve a problem down the road. Have a great night, and I'll see you guys in class.